All right. Good afternoon, Denmark and Carlo, and to everyone watching this recording. So now this would be, I think, the last day for Math 155 or regular meeting natin. Pero meron pa kayong dalawang utang sa akin. Problem set number 4 and the final project. So problem set number 4 came live in Canvas earlier this morning at 8 a.m. So hopefully you guys already downloaded a copy of it. Let me know if there were problems accessing it. Sana tama yung pagkakaset ko ng problem set. And then please read the instructions carefully. So you need to submit a total of 3 or exactly 3 problems. Number 1 is required, and then you'll need to answer one problem from the derivatives part and another problem from the integrals part. So tatlo yung isasubmit nyo. I think the total is 35 points. So the deadline is right before midnight of December 24th. But again, try to finish it before December 21 para masulit nyo yung bakasyon nyo, yung Christmas break. Spend some time with your families and rest. Pero yun nga, alam ko marami kayong tinatrabaho. So kung hindi talaga kayang tapusin right before we hit the Christmas break, sige, magsasacrifice yung 155 natin. Pwede kayong mag-submit hanggang December 24 right before midnight. And then on Monday, I will upload on Canvas the guidelines for the final project. So siguro magkakaroon ng dalawang parts yung final project. Sige, spoil ko na. Yung unang part would be a class evaluation. So, oh, by the way, I think sa SAIS, meron ng student evaluation of teachers. So I highly encourage you guys to answer the student evaluation, especially for Math 155 in SAIS para magkaroon naman ako ng feedback and an official report to the university of how I handled the Math 155 for this semester. Then also dun sa final project, yung first part niya ay magsasagot kayo ng isang online form. Probably it would be a Google form. This is just for me. I will write an evaluation instrument about your experience in Math 155. Your grade will not depend on the content of your answers. It will just be kailangan nyo lang siyang sagutan. Okay? So, regardless of whatever your answer, i-bash nyo ako doon, purihin nyo ako doon, you'll get the same number of points para dun sa Google Form. So, para lang siya, malaman ko kung paano ko pwedeng i-improve yung way of handling online classes or classes in general. Kasi matagal siguro yung feedback sa amin nung SET na via SAIS. So, mas okay na meron akong sariling immediate feedback from you guys. And then the second part of the final project will be like a term paper or a what do you call it? A terminal report of what you did in Math 155. So parang ikukwento nyo kung ano yung experience nyo sa Math 155, ano yung mga natutunan yung bago mula sa 155 compared to what you already learned in calculus, what are the nice points or the nice things you like about 155, what are the rooms, what are the possible room for improvement that you have seen. So yun yung content ng term paper. So it's more of like parang sinasummarize nyo yung naging Math 155 journey nyo sa buong semestre. So you will have free reign over it, pero para tulungan kayo pagsusulat ng term paper na yon, maglalagay ako ng konting mga guide questions, pero you can go over and above the guide questions that I will put in there. Pwede kayong magdagdag, pwede kayong magkwento, i-share yung mga personal experience nyo or anything under the sun that you want to say. Pero yun nga, at least sagutin nyo yung mga nandun sa, yung mga guide questions na ibibigay ko. Then you can put some additions to it. No number of pages required, no format required. So bahala na kayo paano nyo siya isusulat. You can submit it as a handwritten report. You can submit it as a word processed or a computer processed report. So bahala na kayo. So that's why sabi ko, in less than a day, kaya nyo tapusin yung final project. So with problem set number 4 and the final project submitted, wait a couple of days para mag-gradean ko sila. Depende rin sa magiging grading workload ko. But I'll try to grade it as soon as possible para makita nyo na kay Canvas yung final score nyo. And since the semester is nearing its end, paki-double check yung mga entries kay Canvas. Kasi kung ano yung grade nyo kay Canvas, yun yung isusulat ko sa grade sheet. So hopefully I already graded everything. So kung sa Canvas kayo lagi nagpapasa, so dapat kompleto yung score nyo kay Canvas. if there were instances that you needed to submit a homework or a problem set to me via email or via chat, siguraduhin nyo na nag-gradean ko na sila, tapos yung score nyo nasulat ko kay Canvas. Kasi again, ang grades nyo, magiging basehan ko yung computations ni Canvas. Alright? So make sure you double check that kasi otherwise, that would be the final grade that I will put into your into the grade sheet. Okay? So with that out of the way, then I think we can continue on and look at the last few topics for Math 155, Advanced Calculus. So last time we talked about the Riemann sum, and we noted that the Riemann sum is nothing more but a generalization of the lower and upper sums that we had been talking about since the beginning of our development of the Riemann integral. Dun sa upper sum, ang kinukuha nating function values ay yung supremum over each of the subintervals chosen. Meanwhile, for the lower sums, ang pinipili nating function values to be in this summation are the infima over the different subintervals determined by the partition inducer. All right? Etong Riemann sum, tinatanggal niya yung pagpili ng maxima at saka minima on the subintervals. So pumipili lang tayo ng isang random function value, or we're choosing an arbitrary element of the subinterval, tapos yung function value niya yung ginagamit natin pagbuo ng sum. And the sum so constructed is what we call a Riemann sum. So with this definition, you can think of the lower and the upper sum to be specific cases of the Riemann sum. All right. But nevertheless, whether you choose the maxima, the minima, or an arbitrary function value over the respective subintervals, Darbo's theorem, Theorem 5.6 for us, tells us na kung integrable yung function, then yung Riemann integral ay magiging equal dun sa limit ng Riemann sum as the number of partition inducers or the number of elements of the partition inducer increases without bounds. So yung limit ng Riemann sum, habang dumarami yung elements ng partition inducer P, ay equal dun sa Riemann integral. And consequently, since f is integrable over the interval AB, then we say na yung integral ay equal din sa lower ay equal sa supremum ng ng lower Riemann sums at equal sa infimum ng sums. So basically, we can conclude this equation here. Okay? So yung kung si f ay integrable sa closed interval AB, yung Riemann integral ay equal sa limit ng upper Riemann sums, limit ng lower Riemann sums, at equals sa limit ng arbitrary Riemann. Okay? Now, I left the proof of Darbo's theorem to you as a reading assignment. And I hope yung ginawa natin since I think late last week na binabasa natin yung proof and we are just inserting the little details inside the proofs will now makes you familiar with how to read mathematical proofs na existing, which is a nice skill to have, especially if you're reading math books, all right? So kung paano magbasa ng proofs, I want you to practice it for Darbo's theorem. Saka may mga idadagdag pa akong reading assignment na proofs today, specifically sa properties ng Riemann integral. Pero meron tayong mga babasahin ng mga proofs, tapos we will also try to insert some tiny details for those proofs. All right. Tapos you do the same for those proofs that I will leave to you as reading assignment. Okay. Oh, by the way, guys, I again made a batch of corrections of typo errors in the lecture notes, so you can revisit the Google link for the word text or for the lecture notes. Paki-download yung latest version ng lecture notes 5. Pero minor typo errors lang naman yung binago ko doon. Okay? Now, I promise we'll start with example 5.11, which tells us a nice way of evaluating limits of sequences using the concept of the Riemann integral or the Riemann sum. So, ang gagawin natin dito ay, meron tayong sequence. Usually, they are written as summations, all right? Or kung sa Math 38, kung matatandaan nyo, parang tinitingnan natin ito as convergence ng mga infinite sums. Tapos, kaya nating computein using the concept of the Riemann sum and the limit of the Riemann sum being the Riemann integral, yung value kung saan nagko-converge yung sequence of partial sums. Or in other words, kung saan nagko-converge yung mga infinite series. Okay? Now, tingnan natin sa 5.11. Tingnan natin yung sequence of ANs where each of the ANs looks like this. 1 over n plus 1 over n plus 1 plus 1 over n plus 2 until 1 over 2n as n approaches infinity. Now we can take advantage of a nice way or a clever way of writing a sub n that is expressing it as a Riemann sum. Tapos we'll take advantage of the fact that the limit of the Riemann sum is equal to the Riemann integral. And then we will cite some things that we learned from elementary calculus kung paano mag-evaluate ng Riemann integral. Though medyo pandaraya to ng konti kasi hindi pa natin na-discuss yung fundamental theorem of calculus. Pero just for these two examples, excuse me for doing this, pero gagamitin ko yung paano mag-evaluate ng definite integral na natutunan natin sa math 36, 37, or 38. Okay? Now, as I've mentioned, gagawin natin, isusulat natin yung a sub n in a nice way. Ipoporma ko siya na isang Riemann sum. Tapos, pag nasulat ko na siya sa Riemann sum, pwede kong kunin yung limit, magkakaroon ako ng Riemann integral. All right, so it will just be a clever way of rewriting a sub n and taking the limit of a sub n as n approaches infinity, disguising it as a Riemann sum. Okay? Now for this, tingnan natin si a sub n. In sigma notation, a sub n can be written this way, right? So when n is equal to 1 or when I is equal to 1, this guy will be n plus 1. Actually, tama. Yeah, burahin natin to, sorry. Yan, isa sa mga typos na hindi ko pala na-correct. A sub n should just be 1 over n plus 1 plus 1 over n plus 2 until 1 plus 2n. 1 over 2n. Para maging totoo itong formula na ito. So kailangan ko siyang i-correct mamaya ulit dun sa final version ng lecture notes. So that a sub n can be written as the sum of 1 over n plus I going from 1 to little n. So ang first term nito happens when I is equal to 1. So we'll have n plus 1 in the denominator. So dito tayo dapat mag-start. Plus 1 over n plus 2 when I is equal to 2. And so on. When I is equal to n, the upper limit of the sum, this guy will be 1 over n plus n. So that's the terminal term in our finite sum over there. Okay? So maging 1 over 2n siya. Tapos ngayon, again, isusulat ko si a sub n na formang isa siyang Riemann sum. So una, para maging Riemann sum siya, di ba dapat ang maging itsura niya ay summation ng f of c sub I times delta x sub I. Alright? So kailangan ko ng step size. And to make our lives easier, we want delta x sub I to be constant among all of the i's to facilitate the further simplification of the expressions. So yung Riemann sum, hindi necessary na regular yung partition. Pero for the sake of convenience or ease of computation, pipiliin ko yung mga delta x sub I to be a nice number, a constant number all throughout the interval. So for any I, pipili ako ng constant na delta x. And the usual choice would be to choose delta x to be 1 over n. So ibig sabihin, meron tayong interval AB, alright? So pipiliin ko siya na mag-start na yung length ng bawat sub-interval ay 1 over n. Alright? And then, so para magkaroon ako ng 1 over n dito, kailangan kong siyang i-factor out galing sa 1 over n plus I. And whatever will remain will be the function value. Okay? Now, paano ko to gagawin? So para nag-factor out lang ako ng n sa denominator. If I factor out an n from the denominator, so I will have n times 1 plus I over n. So I'll get this new denominator. And if you multiply out the denominators, we'll be back to n plus I. So that's one way to check that you had the right factoring. Okay. So and then now this one or this factor here will serve as our f of c sub I. Yan yung function na i-consider natin. Pero remember, c sub I should be a number in one of the subintervals. Now, what I will do is, with the choice of 1 over n as my delta x, pwede kong i-consider yung interval 0, 1, the unit interval 0, 1, which is fine kasi ang delta x natin ay 1 over n, length ng bawat subinterval ay 1 over n, tapos ang n natin, or meron tayong n subintervals, so the total length of the interval under consideration will be 1 over n times n, which is equal to 1. Kaya alam ko, unit length yung interval na kinoconsider ko. Tapos, paano ko mapipili ng maayos si c sub I? Tingnan nyo yung function f. Yung function f ay 1 over 1 plus I over n. So, ang nakadepende lang na term kay I or na expression ay yung I over n. So, pwede kong piliin si C sub I, okay, to be the I over n's. And this fits well into our framework of writing A sub n as a Riemann sum. Kasi nga, bawat subinterval na kinoconsider natin ay may length na delta x, which is 1 over n. So, kung idodrawing natin yung partition, ito ay 1 over n, ito ay 2 over n, ito ay 3 over n, 4 over n, hanggang makarating tayo sa n over n. Alright? Tapos, sure ako na yung c sub i's ay magbe-belong sa ith subinterval. For instance, the first subinterval here is the interval 0 to 1 over n. And definitely, I equals 1, so 1 over n belongs to the first subinterval. The second c sub I, according to our framework, is 2 over n. And luckily, 2 over n is a member of the second subinterval. Siya yung right endpoint ng pangalawang subinterval. So in this particular framework, maganda yung pagkakapili natin ng delta x, maganda yung pagkakapili natin ng c sub i's kasi nga etong summation na to is exactly of the form of a Riemann sum, where the c sub i's are chosen to be the right endpoints of the nth subinterval. Okay? And the function we are considering is 1 over 1 plus x. So yung x natin dito ay I over n. Okay? So everything's good so far? I think in the problem set, you need to do something similar with it. I'm not sure if the solution will be very similar to this one, pero limit ng sequence din ng mga summation yung makikita nyo sa isang problem dun sa integral part. So probably can try if the same formulation will work for that. So yeah. Okay, everything's good so far? So now we know that A sub n can be written as a Riemann sum of this form. So now, pwede kong sabihin etong expression na to ay isang Riemann sum. And then I will apply Darboux's theorem. Okay? Sabi ni Darboux's theorem, kunin ko yung limit ng Riemann sum. Okay? But the limit of the Riemann sum is actually also the limit of A sub n as n approaches infinity, which the problem asks us to compute for. All right? Tapos, by Darboux's theorem, section 3, alam ko na etong limit na to ay equal sa definite integral ni f over the interval 0 to 1. Okay? And then ito yung sabi ko kanina na kailangan nyo akong i-excuse for a moment, though hindi pa natin na-prove na ang integral ni 1 over x plus 1 from 0 to 1 ay equal sa ln 2, because there we will need the fundamental theorem of calculus. But for now, let's agree that that is equal to ln of 2, all right? And since that is the integral of 1 over x plus 1 over the interval 0, 1, which in turn is the limit of the Riemann sum, or any Riemann sum, as the number of subintervals approach infinity, then that is also the limit of A sub n as n approaches infinity. Okay, so equals siya kay ln 2. All right, so that's one clever way of how to use Darboux's theorem. in evaluating limits of sequences, in particular kung saan nagko-converge yung mga infinite series. Kasi nga yung sequence natin dito ay sequence ng mga partial sums. Okay? Now, another example is in example 12. Medyo mas komplikado yung itsura ni A sub n. But nevertheless, we will employ the same trick. We'll try to write it in the form of a Riemann sum. Okay, so a little bit of algebraic manipulation here. I guess here we're still using the interval 0, 1, the unit interval 0, 1 as the integration interval. All right, because I can write A over n as this summation. Okay, tapos okay. Tapos, gagamitin ko si 1 over n to be my what? To be my delta x, all right? Regular partition din yung gagamitin ko. So, ititira ko tong n na to. Tapos, ilalabas ko yung mga constant factors para mas simple yung calculation. So, we can rewrite this guy using properties of radicals as this one, okay? And then nth root of square root of e to the n, nth root of e to the n is equal to e. So nakalabas si e. Tapos si 2 ay ilalabas ko rin. So doon ang galing yung 2 over e. Retain ko si 1 over n. So ang natira na lamang ay si 1 over this guy. Okay? And we can write the nth root of e to the 2i as 1 over e to the 2 times I over n. And then this guy will give us f of c sub I. So that means we can choose the c sub i's to be still I over n, which again perfectly fits our framework. Kasi nga, ang step size ko ay 1 over n. If I will assume that I am in the unit interval 0 to 1, so ibig sabihin si I over n is a perfect candidate para maging yung c sub I dun sa Riemann sum na ifo-form natin. Actually, it turns out that the c sub i's that we are using are the right endpoints of the integration subintervals. Okay? Tapos, yung f of x natin dito ay magiging 1 over e to the power 2x. Okay? Kasi nga yung x nating pinipili ay yung mga c sub i's which are the I over n's. All right? And again, we will appeal to Darbow's theorem, section 3. Pagkuha ng limit ng a sub n, napakita natin na si a sub n, pwede nating isulat in this manner. And further algebraic manipulations will lead us to this expression over here. And we noted that this guy is of the form of a Riemann sum, whose c sub i's are chosen to be the right endpoints. So ito yung itsura niya. And then Darbow's theorem says that the limit of a Riemann sum is equal to the definite integral over the integration interval chosen, right? Now, in this case, we chose the unit interval 0, 1 as the integration interval. So this guy will converge to, or this guy, the a sub n's, will converge to 2 over e times the definite integral of 1 over 2 to the power, 1 over e to the power 2x as x goes from 0 to 1. All right. You can further write it as 2 over e integral from 0 to 1 of e to the negative 2x dx. And then you can solve this using the good old familiar substitution or integration by substitution. You can let u be equal to, I think, negative 2x. du is negative 2 dx. And then it can be evaluated easily. All right. So I leave the rest to you, but I hope you got the idea how to translate a sequence of partial sums into a sequence of Riemann sums, which we know will converge to the integral of a function f over the interval ab, provided that f is integrable on the closed interval ab chosen. And usually our choice of closed interval is the unit closed interval from 0 to 1, giving us step size I over 1 over n. Okay? So I hope that's fine. I don't know if this is illustrated in math 36 or 38. So siguro nakita niyo na sa 38 ay what? the integral test for convergence of sequences. For the convergence of series. Pero yung principle behind that is something like this. It depends on the convergence of a definite integral. Okay. Now that ends chapter 5.2. Now we will briefly go into section 5.3, which enumerates some properties of the Riemann integral. But we will state some of the basic properties that you already knew from Math 36. Actually, probably some of them were also proven in Math 36. So yung susunod na Theorem 5.8 ay iiwan ko na sa inyo as a reading assignment. The proofs were given in the work text, so kindly read it. But we'll focus more on Theorem 5.7, which will play a role probably in the proof of some parts of 5.8 or the algebraic properties of the integral. Pero maganda kasi yung proof nito. Nagdedepende lamang siya dun sa integrability criterion. Okay? So let's see what Theorem 5.7 says. So we assume that f is a function or is a bounded function from the closed interval AB into the set of real numbers. And we let C be a number strictly between A and B. So interior point ni open interval AB si C. Then if f is integrable on the then f is integrable on the closed interval AB if and only if f is integrable on the closed interval AC and the closed interval CB. So you can think of Theorem 5.7 as the additive or the additivity of the integral operator. So ibig sabihin, pag meron kang interval AB, dito na lang. Okay? Tapos kumuha ka ng interior point C dun sa loob ng interval, yung function mo na f ay magiging integrable dun sa buong interval AB if and only if the function is integrable on the two subintervals induced by the number C. So it must be integrable on the closed interval AC and the closed interval CB. And the proof is not that hard. It will just bank on the integrability criterion. Remember, the integrability criterion says that for any given epsilon greater than 0, we must find a partition inducer such that the upper Riemann sum minus the lower Riemann sum with respect to that partition inducer is less than epsilon. So basically, ang sinasabi sa atin ng integrability criterion na yun ay we can make the difference between the upper Riemann sum and the lower Riemann sum arbitrarily close to each other, thereby making their infimum and supremum respectively equal to each other. Okay? So tingnan natin yung proof. Tapos yun lang yung actually gagamitin ko, Theorem 5.1, a nice play on the epsilon p challenge doon sa integrability criterion. Okay, so let's start with the forward direction. So we will assume that f is integrable on the closed interval AB. Tapos gagamitin ko nga yung integrability criterion, Theorem 5.1. Pag si f ay integrable, then given any epsilon greater than 0, however small, there will exist a partition inducer P of the closed interval AB such that the upper Riemann sum minus the lower Riemann sum will be less than epsilon. Okay? And we know this guy is a positive number kasi nga yung upper Riemann sum ay laging mas malaki sa lower Riemann sum. So this is still a small positive number, smaller than the arbitrarily small epsilon chosen before. Okay? Now, here I can assume that, or without loss of generality, that C is an element of the partition inducer P. Kasi kung si C ay hindi kasama kay P, alright? So kung si C ay hindi isa dun sa mga partition points o hindi siya member ng partition inducer P, so pwede kong idagdag si C dun sa partition inducer P. Kasi nga kapag nagdagdag ako ng isang element, makakakuha ako ng isang refinement ng partition inducer. Kasi ang problema ko rito, hindi ako sure kung si C ay nasa partition inducer P that was the response to the epsilon. Okay? Pero I will say that it doesn't matter kasi nandun man siya o wala, totoo pa rin tong inequality na to. Kasi kung wala si C dun sa partition inducer P, pag dinagdag ko si C kay P, magkakaroon ako ng refinement ng partition inducer P. Tapos alam natin, pag meron tayong pag meron tayong refinement ng partition inducer, mas lumiliit yung upper sum. Okay? So halimbawa si P star, tawagin ko siyang P union the set containing C in the case that C doesn't belong originally to P. So P star is a refinement of P. Remember, may result tayo dati na kapag nagiging mas maliit yung upper sum kapag meron kang refinement ng isang partition inducer. So this guy will be smaller. Okay? Pagka ni-refine ko si P. Tapos, kabaligtaran na naman yung nangyayari sa lower Riemann sum. Kapag nagdagdag ka ng isang element dun sa partition inducer, nagiging mas malaki yung lower Riemann sum. Okay? So, the lower Riemann sum of a refinement is larger than the lower Riemann sum of the original partition inducer. So, ano nangyayari dito? Lumiliit yung minuend, lumalaki yung subtrahend, so yung upper Riemann sum minus lower Riemann sum with respect to the refinement of the original partition inducer is smaller than the original difference. Dahil yung original difference ay mas maliit kay epsilon, yung upper minus lower dun sa partition inducer na refinement ng original na given ay magiging mas maliit din kay epsilon. But still that new difference, UF P star minus LF P star ay positive pa rin. Kasi nga yung upper Riemann sum laging mas maliit sa lower Riemann sum for any partition inducer. Mapa-refinement man yan o hindi. Okay? So totoo pa rin tong inequality na to para kay P star kung isasama ko kay C. So it doesn't matter if C is inside of that or not. Okay? Pero kakailanganin ko kasi yun later dun sa proof. So okay lang na i-assume natin na si C ay partition inducer ni P. Okay? Bakit ko gustong si C ay maging part ng partition inducer na P? Kasi i-define ko si P1 as the partition inducer P intersection A, C, and I think hindi ko pa rin to na-correct dun sa last version. Sorry about that. Ito ay P2, P sub 2. Siya dapat yung P intersection C, B. So ang ginawa natin dito ay parang hinati ko yung partition inducer na P. Hinati ko siya sa dalawang parte. Yung mga partition inducers na nakay P pero nandun sa closed interval AC. Tapos yung partition inducer ay yung mga elements ng partition inducers na nandun naman sa kabilang interval C, B. So, kaya crucial na si C ay maging isa dun sa metal P. Bakit? Kasi only then will P1 be a partition inducer for the closed interval A, C. Gusto ko si P1 maging partition inducer ng closed interval A, C. Tapos remember, required na dapat yung right endpoint interval ay isa dun sa mga elements ng partition inducer. Alright? Kaya dapat si C maging isa dun sa mga elements ni P para maging element siya ng intersection which is P1, thereby making P1 a partition inducer interval A, C. Tapos ganun din yung para kay P2. Kaya dapat si C talagang element ng P. Alright? Tapos ano ba yung goal ko rito? Bakit naghati ako ng dalawa? Kasi nga, gusto kong ipakita na integrable si F sa closed interval AC at sa closed interval CB rin. Alright? So ngayon, gagamitin ko para doon ay yung integrability criterion pa rin. Kasi meron na tayong issue kanina or meron na tayong challenge na epsilon greater than 0. Napakita natin na sa buong interval AB, meron nag-exist na partition inducer P. Kasi nga si F ay integrable sa closed interval AB. Ngayon, gusto kong ipakita si F ay integrable dun sa dalawang mas maliit na subintervals. So dun sa epsilon na yon, kailangan ko makahanap, which is arbitrary. So I can use the same arbitrary epsilon. gusto ko makahanap ng partition inducer ni AC at partition inducer ni CB such that this inequality restricted to those two partition inducers is still true. Okay? Tapos ang hula ko o ang claim ko, si P1 ay yung sagot na partition inducer para dun sa epsilon sa closed interval AC. Tapos si P2 naman yung partition na sagot dun sa challenge epsilon para dun sa closed interval CB. Alright? Now, how can I work it out? Well, kailangan kong munang i-note kasi kulang to. Parang bigla niya na lang sinabi na, okay, totoo yung gusto mong ipakita. Pero kung ipapaprove ko to sa inyo, kailangan ko yung intermediate step. How did you come out with this equality or this inequalities? Kasi ito yung gusto nating inequality. Sila yung sasagot sa integrability criterion. Okay? So you need to insert some of the details. So parang ganito, nakahanap kayo ng proof sa internet pero may mga detalye na kulang, so kailangan nyo siyang idagdag. Okay? Ang alam natin ay ito. From the assumption, okay? So we know that UPF, so epsilon is larger than UFP minus LFP. Okay? Pero ngayon, alam natin na si P ay kaya nating paghiwalayin sa dalawang sets P1 and P2. So it is easy to see that the upper Riemann sum of F with respect to the partition inducer P can be written as the upper Riemann sum of F relative to the partition inducer P1 plus the upper sum of F relative to the partition inducer P2. Alright? Kasi si P1 union P2 siya ay equal kay P. Minus, ganun din yung gagawin kong argument para dun sa lower Riemann sum. Lower FP1 plus lower FP2. And I know that this guy, or this guys, is less than epsilon. Alright? Is that good so far? Tapos, i-group ko ito in a nice way. So I'm gonna write it further as, i-regroup ko lang naman yung mga terms niya. Upper Riemann sum with respect to P1 minus lower Riemann sum with respect to P1 plus upper Riemann sum with respect to P2 minus lower Riemann sum with respect to P2. Okay? Tapos, ito pa ring sum na to ay mas maliit kesa kay epsilon. Alright? Now, what do we know? This guy is positive. This guy is also positive. Because again, the difference between the upper and the lower Riemann sum is always positive. Or always non-negative. Alright? So ito ay non-negative, ito ay non-negative. Ang sum nila ay less than epsilon, which is a positive number. Then either of these two guys, or actually both of them, will be less than epsilon. So ito, magiging mas maliit kay epsilon. Ito, magiging mas maliit din kay epsilon. And that's what this is, kung ano yung nakasulat dun sa lecture notes. And again, this guy is less than epsilon, right? So sa kahit anong epsilon na nabigay, ito, with respect to the partition inducer P1 of the closed interval AC is less than epsilon. So by Theorem 5.1, the integrability criterion, we can say that F is Riemann integrable on the closed interval AC. And similarly, by virtue of this guy and the integrability criterion, we can say that F is integrable on the closed interval C comma B, proving the forward part of our characterization theorem. Okay? Now, conversely, ganun din naman yung sa converse, similar arguments, integrability criterion din yung gagamitin ko, iba nga lang yung pagsisimulan ko. Magsisimula ako dun sa assumption na si F ay integrable dun sa dalawang mas maliit na intervals. And I want to show that F is integrable on the union of these intervals, which is the closed interval A comma B. But again, our assumption is that F is integrable on these two closed intervals right away. So we can appeal to the integrability criterion and conclude that for any epsilon, however small it is, there exist partitions P1 and P2 of the closed interval AC and closed interval CB respectively, such that these two inequalities is true. Tapos feeling ko alam nyo na yung mangyayari. Ginawa kong epsilon over 2, saka epsilon over 2 yan instead of epsilon. So you might be thinking, alam ko na yung gagawin. Ipapag-add yung dalawang sides ng inequality. All right? And that was true. Because again, there is a challenge issued for an epsilon greater than 0. So, kailangan ko makahanap ng partition inducer ng closed interval A comma B such that the upper minus lower Riemann sum will be less than epsilon. Pero madali na siya, gagamitin ko na yung na-establish natin na P1 at saka P2 from the assumption. Okay? Now, to get the response P, partition inducer P, sasabihin ko, madali lang yan. Si P ay yung union ng P1 at saka ni P2 na alam na natin nag-e-exist kasi nga si F ay integrable dun sa dalawang mas maliit na intervals. Alright? So that means, yes, you add the two sides of the equation, this guy plus this guy, using the same argument as we used here, siya ay magiging equal sa upper Riemann sum ni F with respect to the partition inducer P. Tapos yung minus L FP1 minus LFP2 ay equal lamang sa LFP. Again, gamit yung argument natin kanina. And then epsilon plus epsilon would be epsilon. And so we get this. The upper Riemann sum and minus the lower Riemann sum can be made arbitrarily small. Therefore, by the integrability criterion, F is integrable on the closed interval A comma B. All right? So, any questions? Sana ganito lang kadali mag-prove, no? Kasi parang dinidiscuss natin to, napakadali, napaka-straightforward. Pero pag tayo yung gagawa, siguro it will take some preliminary analysis, some amount of thinking before we can write an elegant proof such as this one. So, don't worry, kung medyo natatagal lang kayo mag-prove, ganun talaga sa analysis. Mas mahaba-haba yung pag-iisip ng proof kaysa dun sa pagsusulat ng actual proof, right? So, maganda lang yung presentation ng nasa lecture note kasi napaghandaan na nila yan nung sinulat nila ito. All right? Now, there is an additional statement here. If f is integrable on the closed interval a, b, then this equation is true. So ito yung additivity ng integral. So pag hinati mo yung closed interval a, b sa dalawang parte, dalawang disjoint parts, then the sum of the integrals over those two disjoint parts ay equal dun sa integral ng dun sa buong interval. All right? So paano siya nangyayari? Well, it will be a play on the inequalities involved. All right. So just remember, we have this inequality. We know this is true because f is integrable on the closed interval AB. Ito yung gusto nating ipakita. Now, for an arbitrary epsilon greater than 0, okay? Ito yung mga alam natin. Si f ay Riemann integrable, so this guy is well defined, so I can start with this. Alam ko ito ay infimum ng mga upper sums. This is the greatest lower bound of all the upper sums of f with respect to all possible partition inducers. All right? So definitely this would be less than or equal to the upper sum by it being the infimum. All right? Tapos coming from here, the upper Riemann sum is always less than epsilon plus the lower Riemann sum. So nilipat ko lang to dun sa kabilang side ng inequality. And I will get this upper Riemann sum less than LFP plus epsilon. Okay? Now, I can write this into as a sum of two lower Riemann sums. So P1 and P2 will be the intersection of P with a closed interval AC and a closed interval CB respectively. So parehas lang yung definition ni P1 at ni P2 as what we have earlier. So etong si L, with respect to P, nahati ko sa dalawa. Tapos, kinopya ko lang si epsilon papuntang ron. Why do I want to have that? So, may typo dyan. Nakorek ko na to, nabura ko na yung inequality sa final version. So, this guy, ito ay lower Riemann sum. Pero ang Riemann integral ay supremum ng mga lower sums. So ibig sabihin, upper bound ng mga lower sums yung Riemann integral. So ibig sabihin, this guy is smaller than this integral. Similarly, this guy is less than or equal to this integral. And then I'll just carry over the epsilon over there. And we have this inequality now. So in summary, what we have shown is the Riemann integral of f over the interval AB is less than this guy. Okay? But this inequality is true sa kahit na anong epsilon greater than 0. Mas maliit siya sa lahat ng epsilon, totoo ito sa lahat ng epsilon na greater than 0. So definitely, we must accept that the Riemann integral over the interval AB is less than this guy. Alright? Pwede mong i-drop yung epsilon kasi si epsilon ay lahat yan ng positive real numbers, however small they are. So essentially, this must be true. I think we have a theorem like this at the beginning of the class or during the middle of the semester. So yeah, kindly look at that again. Pero ano yan, usual tricks analysis. Pag arbitrary si epsilon, tapos nasa inequality siya, pwede mo siyang i-drop. Kasi nga totoo naman siya sa lahat ng epsilon greater than 0. So baliwala yung nadadagdag niya. All right. And then using the same argument, similar argument, tingnan mo naman yung pakabila kasi napakita na natin yung less than relation dito. Gusto ko naman ipakita na greater than or equal. Alright? Para ma-prove yun, same argument. Okay? Mapapakita mo na yung sum ay less than or equal kay dito. Alright? And that is true for all epsilon greater than 0. So that means this guy is true. So napakita na natin yung less than or equal to at saka yung greater than or equal to. So ibig sabihin equal itong dalawa na ito. So again, this is the additive property of integrals. All right? Now this is very useful. I think this is the stepping stone for some of the proofs of the algebraic property of integrals, namely some of those written in Theorem 5.8. Again, some of these results were already proven in Math 36, but here in the lecture notes, a Math 155 proof for these statements were given. So, and they will be reading assignments for you guys. So, tingnan lang natin ano yung ibig sabihin ng mga theorems na to. Number one, the Riemann integral of a sum is the sum of the Riemann integrals. The Riemann integral of a scalar multiple of a Riemann integrable function is a scalar multiple of the Riemann integral of the function f. Okay. Tapos ito ay isang mahalagang property. So if f is bounded below by m and bounded above by big M, then the integral of f over the interval AB will be bounded below by m times the length of the interval and bounded above by capital M times the length of the interval. So ito yung parang order property ng integral. So pag bounded si f, yung integral ay magiging bounded nung parehong bounds times the length of the interval. Right? Tapos we have another order theorem for integrals. Kapag kasi Okay, yeah. Kapag si f ay less than or equal to g, and this is a shorthand notation for saying that f of x is less than or equal to g of x for all x in the interval AB, then the integral of f is less than or equal to the integral of g. Right? Pag laging mas malaki yung function f, pag mas maliit si function f kaysa kay function g over the entire closed interval, ibig sabihin mas malaki yung definite integral ni g kaysa sa definite integral ni f. Right? So I think this is easily illustrated using the interpretation of integrals as areas under the graphs of f and g, but above the x-axis. And then finally, If f is integrable, then the absolute value of f, which is defined to be the function that assigns to x the absolute value of f of x for all x in the interval a, b, is also Riemann integrable. And in fact, the absolute value of the Riemann integral of f is less than or equal to the Riemann integral of the absolute value of f. Actually, f is a theorem E or section E of the theorem is very useful in measure theory. So madalas ginagamit ito to prove integrability of some functions. Okay? And you can think of it as some sort of a generalization of the triangle inequality. All right? Kasi di ba yung summation, pwede nyo siyang isipin na sa sum. So ang absolute value ng sum ay laging mas maliit sa sum ng absolute values. The same goes true for integrals, which is sort of a generalization of the summation operator. Okay? So again, the proofs of these statements are over here. So reading assignment na lang sila. Hopefully, nakuha nyo na yung training sa pagbabasa ng mga proofs. So, iwan ko na yan sa inyo. Okay, yes, Carla, you have a question?
Sir, question lang. Yung sa item A, is that a typo yung sa dulo?
Yes, Carla, thank you. Siguro na-copy-paste to, no? Ano nangyari? Daming typo, no? Ito ay A, B, tapos ito ay G. Okay, thank you, Carla. Hopefully, I'll remember it later pag in-edit ko na siya. Sige nga, lagyan ko na siya ng malaking star para pag-edit ko mamaya maalala ko. Alright, what else? Okay. Kung may mga nakita kayong typo, paki-send na lang ako ng email or chat para ma-correct natin yung lecture notes. Alright. Okay. Okay. Now, we have two important results left for the course. The first one is the mean value theorem for integrals. Theorem 5.9 is a generalized version of the mean value theorem for integrals. So, ang sabi niya, kapag ka si f ay continuous sa closed interval AB, tapos, so si f ay continuous, so ibig sabihin alam natin na siya ay, di pala natin alam kung siya ay bounded, no? So hindi ko masabi kung siya ay integrable or not. But actually, the integrability of f is not required here. So, yeah, sufficient na si f ay continuous. Tapos si g dapat ay integrable on the closed interval AB. And that g of x is greater than or equal to 0 for all x in the closed interval AB. Pag nasatisfy yung mga premises na yon, ang sinasabi sa atin ng MVT para sa integrals, yung integral ni f times g over the interval AB ay equal sa f of c times the integral of g over the interval AB for some c in a closed interval A comma B. So ibig sabihin may mahanap tayong element ng closed interval AB such that yung integral ng product ay equal sa function value nung f under that specific number c, which unfortunately the MVT doesn't tell us exactly sino si c. Ang sinasabi niya lang, maghanap ka kasi sure na meron sa pagitan ni A and B. Hindi ko alam kung sino, pero sure ako meron. Yun yung sinasabi ng MVT. Such that pwede mong ilabas yung f of c tapos integral ni g. Actually, there's an implicit conclusion or implicit result in this statement of the mean value theorem. Kapag kaya pala daw si f ay continuous, tapos si g ay integrable, ibig sabihin yung integral ni f times g ay, yung function f times g ay integrable na rin. So, ang product ng dalawang integrable function ay integrable. Pero ang product ng isang continuous function, which we don't know if it is bounded or not, all right, times another integrable function ay integrable din. And that integral is equal to a function value under f times the integral of g. Kaya kung babasahin niyo yung theorem, mahalaga yung integrability ni f. mahalaga yung integrability ni G. Kasi yung right-hand side niya ay integral ni G. So dapat mag-exist itong integral na to. Tapos yun nga, dahil yung f of c naman ay nag-exist kasi ano daw si C? Si C ay isang number sa closed interval AB. Tapos si f ay continuous. So ibig sabihin si f defined sa buong closed interval AB. So this number is well-defined. The product is well-defined. So the integral is well-defined. Kung totoo yung mean value theorem. And actually, totoo siya. Papakita natin in a few moments. Pero siguro hindi ito yung usual mean value theorem na nakita nyo mula sa Math 36. Sa Math 36, ang version natin ng mean value theorem ay si gi equal kay 1. The constant function 1. So because when g is the constant function 1, so this is g of x equals 1 for all x in the closed interval AB, then this statement of the mean value theorem simply says this is the integral from a to b of f, okay, ay equals f of c times integral ni 1 over the interval AB. Pero ano yung integral ni 1 over the interval AB? That is just the length of the interval AB. So that's gonna be b minus a. And then pwede kong i-divide both sides ng b minus a. Ito yung makukuha ko. Okay? So there exists a number c that is equal to the average value of f over the interval AB. Ito yung sinasabi natin na average or mean value ni f over the interval AB. Bakit siya yung average value? Kasi nga yung integral parang siya yung infinite version ng summation. So sum ng mga function values divided by, instead of the number of function values added, divided by the length of the interval kung saan natin kinukuha yung mga function values. So this guy is a generalized version of the average. But this time we are averaging uncountably many function values. Alright? Kaya ang tawag sa kanya mean value theorem. Pero ito, yung generalized, and I think other texts calls this the generalized mean value theorem for integrals, or I think some call it the, if I'm not mistaken, kindly check me on this, the Cauchy mean value theorem for integrals. Okay? And then let's try to prove it. Hindi ganun kahirap yung proof niya. Gagamitin ko lang yung theorem 5.8 section, I think section F yung gagamitin ko. Tignan natin kung mag-work nga siya. Okay, may proof naman dito, sundan natin siya. Okay, assumption. F is continuous on the closed interval AB. Dahil si F ay continuous sa isang compact set, mag-apply yung EVT o yung Weierstrass theorem. Anong sabi ni Weierstrass? F attains its maximum and minimum over the interval AB. Ibig sabihin, merong maximum si F, call it capital M. Meron siyang minimum, call it little m over the interval AB. Okay? So definitely, so ang ibig sabihin yan, si little m ay lower bound ni f of x, the lower bound naman ni capital M for all x in the interval AB, right? And then another assumption that we had is that G is always non-negative over the interval AB. So I can multiply all sides of the inequality by G of x without affecting the inequality symbols. Doon papasok yung assumption na G of x is greater than or equal to 0. So if you do so, we'll get this guy. All right? Tapos, ano na yung susunod? Order property ng integral. One of the theorems from sections of 5.8. Pag in-integrate ko yan, preserved yung inequality symbols. Tapos pag in-integrate ko ito, halimbawa, yung nasa pinakakaliwa, lalabas si m kasi constant yan with respect to x. So ito yung magiging itsura niya. Yung nasa kanan ay integral lamang ng f times g. Tapos yung nasa pinakakaliwa, pag in-integrate ko yan, lalabas si big M nung integral. So matitira lang ito. Okay? Good so far? Alright. Then, ang pinapahanap sa atin ay ano dapat daw si number C. Kasi ang promise ng MVT, there exists a number C in the closed interval AB such that, ayoko nang isulat ulit, such that this equation is true. So we need to find that number C guaranteed by the closed interval, guaranteed to be on the closed interval AB. Right. Meron dalawang cases tayong gagamitin. Unang case ay kunwari si integral of g over the interval AB ay equal kay 0. Okay, makikita nyo bakit to nakahiwalay. Siguro dapat inuna ko yung integral not equal to 0. Pero tingnan natin. Ano yung komplikasyon o ano yung mangyayari kapag ka si g o yung integral ni g ay equal kay 0? Kung yung integral ni g ay equal kay 0, ibig sabihin ito ay 0. Alright? M times 0 ay 0. So 0 yung lower bound. Tapos ito ay magiging 0. So yung M times 0 magiging 0 din. So that means the integral of the product is less than or equal to 0 but greater than or equal to 0. Therefore, this integral must also be equal to 0. Alright? So ito ay equal kay 0. Okay. Tapos si integral ni g ay equal din kay 0. So ibig sabihin, totoo itong equation na to. Itong mahabang equation na i-highlight ko. Okay? Kasi ito ay 0. Alright? Mag-multiply ako sa kanya ng kahit anong number. For instance, I multiply it by f of a plus b over 2. Then, since this equation is true, f of c times the integral is equal to the integral of the product, so the desired c can be taken to be a plus b over 2. Actually, hindi naman siya yung unique choice of c. Kasi nga, 0 na to. So, pwede akong pumili ng kahit anong ilalagay ko sa loob ni f as long as nasa loob siya ng closed interval AB. Pwedeng pinili nyo nga dito si A. Totoo pa rin yung equation. A is in the closed interval AB, then that's fine. That suffices as your choice for C. Pwede rin naman si B. Pwede rin naman kahit anong number na nandun sa closed interval. So it's no biggie when the integral of g is equal to 0. Any number between a and b will suffice as our choice for the number c guaranteed by the mean value theorem. Okay. The complicated case, though it's not that complicated, will be coming from when g or when the integral of g is not equal to 0. Bakit hindi malaking problema yan? Kasi babalikan natin yung inequality na meron na tayo kanina. This guy. Alright? Naghahanap tayo ng value para sa C. Alright? So pwede kong gawin dito ay i-divide ko both sides or i-divide ko all sides by the integral of G. And that where the assumption that G is not doesn't have a zero integral will come into play, right? Dahil yung integral ni g ay hindi equal kay 0, I can divide all sides of this inequality by the integral of g, giving us this new inequality. Alright? Tapos ano yung kagandahan nito? So si m, yung pinakamaliit na value, yung little m, siya yung pinakamaliit na value ni f sa buong interval AB. Alright? Tapos si m, capital M, siya yung pinakamalaking value ni f dun sa AB. And then this number over here, this ratio over here, is between the smallest and the largest value of f on the closed interval AB. Now, f is continuous on the closed interval AB. So, ibig sabihin, sa kahit anong number, sa pagitan ng smallest value ni f at largest value ni f mula sa closed interval AB, the intermediate value theorem guarantees na merong isang number sa closed interval AB na ang function value ay equal dun sa intermediate value na yon. In other words, IVT guarantees the existence of a number C whose function value, f of C, is equal to the middle guy over here. Pero since we have this equation over here, the existence of c is known, you can just multiply both sides again by the integral of g to give us the exact promise of the mean value theorem. Okay? And that ends the proof. At sana na-appreciate nyo ngayon yung mean value theorem, yung intermediate value theorem. Kasi parang sa Math 36, ini-state lang natin yung intermediate value theorem. Siguro from there would be one instance na i-apply natin siya pag prove na merong root ang isang continuous function on a closed interval AB where it attains a positive and a negative number. But beyond that, parang napaka-synthetic o what do you call this? Napaka-contrived? Hindi. Parang napaka-tailored nung IVT na wala naman pala siya, parang wala siyang gamit. Pero the intermediate value theorem is a very powerful theorem that is used to prove the mean value theorem. And you will see later that the mean value theorem plays a huge role in the proof of the fundamental theorem of calculus. Tapos fundamental theorem of calculus siya yung nag-govern or siya yung dahilan kung bakit nakakapag-evaluate tayo ng integrals. So, ganon kalakas yung consequences ng intermediate value theorem. Okay? Now, let's fill in some other gaps in our theory of integrals. So far, paano natin or ano yung saan natin dinidefine yung integral? Dinidefine natin yung definite integral sa isang closed interval AB. And when we say closed interval AB, there's a tacit assumption that A is less than B. Pero di ba minsan nakakita tayo ng integral na yung lower bound ay mas malaki kaysa sa upper bound. So for that, to make it consistent with the brand of calculus that we already know, we will force the issue that the integral of f over the interval AB is equal to the negative of the integral of f from B to A. So in our development, walang paraan para ma-evaluate natin itong integral na to. Kasi it doesn't make sense to have a closed interval B comma A where B is greater than A. Hindi magbe-make sense yon. Walang ganong interval. Okay? So para lang ma-accommodate yung ginagawa natin sa Math 36 and for technical reasons to follow, specifically in the proofs of some results in higher calculus or in measure theory, kailangan nating tanggapin o i-define or i-set by convention that the integral of f over the interval AB ay equals the negative ng integral from B until A. And also, we will define the integral of f over the singleton C, all right? So integral from C to C ay equal kay 0. Okay? Now, this definition will have far-reaching applications, not only are actually far-reaching applications in the theory of measures and theory of integration, all right? Pero isang immediate consequence niya ay dun sa additive property. So dito sa additive property, kung babalikan natin, Theorem 5.7, inassume natin na si C ay nasa pagitan ni A at saka ni B. Now, with definition 5.8, yung definition natin kanina, si C ay hindi na necessarily nasa interval AB. So si C pwedeng nasa kaliwa ni A, si C nasa kanan ni B. And this statement true. All right? So siguro pag-isipan ko, nabigay ko na nga pala yung problem set, no? Ngayon ko na-realize maganda siyang problem sa problem set. Ipakita na hindi lang 'to nagwo-work sa mga C's na nasa loob ni open. Posible rin siya mag-work kahit si C ay nasa labas na ng open interval AB thanks to the last definition that we had. Okay? Okay. Okay pa ba kayo? Or info overload na? Medyo naramdaman ko na rin yung pagod sa monologue na ito. Okay. Pero para hindi na tayo mag-meeting sa Monday as a Tuesday, at ma-devote nyo yung Tuesday pagtatapos ng problem set or for other ACAD works that you might have or for rest kung tapos na kayo, tapusin na natin. Give me probably 10 or 15 more minutes titingnan lang natin ng mabilis yung fundamental theorem of calculus. Okay? And this is the same old theorem that you know from Math 36. Ito yung una, yung section A niya. Siya yung basically nagsasabi na ang integration ay inverse process ng derivatives. Kaya ang ibang tawag sa integral ay anti-differentiation. Now the second section, section B, tells us a nice way of how to evaluate definite integrals. Paano siya kino-compute by the way of computing a antiderivative for the integrand little f. Okay? So balikan natin yung mismong statement ng FTC. Yung part A, ang assumption, si f ay continuous. Kung si f ay continuous on a closed interval AB, then alam natin defined itong integral na to. Okay. So dahil defined yung integral na yan, tapos tawagin natin siyang capital F. Then the theorem is saying that f is continuously differentiable. In fact, the derivative of f, so the derivative of this guy, we will write it by f prime, ay equals sa integrand. Ito yung sinasabi niya na parang reverse process ng integral yung derivatives. Kasi ito ay derivative followed by an integral. They sort of cancels out. So parang yung composition niya magiging identity function. Natitira lamang yung integrand. Okay? For section B, ang assumption natin ay the same. All right? But we will assume that there exists an antiderivative for f on the closed interval AB. Right? So ibig sabihin, kung meron tayong makikita na function big F na ang derivative ay equal kay little f sa buong interval AB, then f is integrable on the closed interval AB. And not just that, the Riemann integral of f over the interval AB is equal to the difference of the function value under f of b minus the function value of a under f. All right, and this is the usual notation we used in Math 36. Okay? Now, tingnan natin, paano pinuprove yung FTC? Parang sa Math 36, hindi yata natin pinuprove yung FTC. Pero simple lang naman yung proof ng FTC. Okay? Part A muna. Pakita natin na derivative talaga ni f si little f. So, parang kailangan kong i-prove itong statement na to. And I can prove this using the definition of the derivative. Okay? So we want to compute f prime, and by definition, f prime of x is the limit of the difference quotient as the increment h approaches 0. So definition lamang siya ng derivative na nakita na natin in Unit 3. Tama nga ba? Unit 3 or Unit 4, whichever one it is, right? Kung saan natin dinefine yung derivative. Tapos pwede ko itong isulat in terms of the integral, okay? Equal to sa limit ng ano si capital F evaluated at x plus h. Remember, capital F is defined to be this integral. So si x papalitan ko lang ng x plus h. So siya yung integral ni f of t dt starting from a until x plus h. Kasi yung argument niya ni x dapat siya yung upper limit. Okay? Tapos minus capital F of x. Siya naman yung integral ni f of t dt simula kay a hanggang kay x all over h as h approaches 0. Okay? Tapos, simplify ko to, no? Pwede kong kunin yung negative sign, gawin ko yung positive, pero by definition ng negative integral, pwede kong palitan yung bounds. Gawin ko siyang bound from yung bound simula kay x papunta kay a. Alright? Using definition 5.8. And then ngayon, pwede kong gamitin yung additivity ng integral. Ito ay integral mula kay x hanggang kay a plus the same integral, but this time from a to x plus h. So by the additive property, pwede ko siyang isulat under one integral. Maging integral na lang siya from, ang daming nabura. Come on. Yeah. Okay, ayaw niya talaga magpabura ng solo. So ito ay magiging x lamang. Alright, by the additive property. And that's what you see here for the expression for f prime. Ito yung makukuha natin. Okay? So, lipat ko lang to rito. Okay. Now, dito, gagamitin ko yung mean value theorem. Gagamitin ko yung mean value theorem dito with G equal to 1. Okay? Diba? Or yung specific case ng mean value theorem natin kanina. So, si f prime ay equals the limit ng 1 over h times the integral. Pero gagamitin ko yung MVT sa integral na to. Ibig sabihin, there exists a C between x and x plus h such that this integral is equal to the function value of f at that number c times the length of the interval. Ano ba yung length ng interval? Interval from x to x plus h. So its length would be x plus h minus x. So that's going to be h. So yung f prime pala ay equal lamang sa limit na ito. Right? But what can we say about that? Well, si h ay palapit ng palapit kay 0. So ibig sabihin, but before that, makakancel ko pala muna yung h. Alright? Now, matitira na lamang ay limit ni f of c as h approaches 0. But note that c is not just any constant. C is a number that depends on h. Bakit siya nagdidepende kay h? Kasi si c ay isang number sa pagitan ni x at saka ni x plus h. Now, we are considering the case that h approaches 0. What happens when h approaches 0? Kapag ka si h ay lumiliit, si x at saka si x plus h ay palapit ng palapit sa isa't isa. Alright? At ano nangyayari kay c kung si x at saka si x plus h ay palapit ng palapit sa isa't isa? Si c ay nasa pagitan ni x at saka ni x plus h. When h approaches 0, when it becomes a very, very small number, then we have no choice but to admit that x is equal to c. Right? So therefore, the limit of f of c as h approaches 0 is equal to f of x. Therefore, f prime of x will be equal to little f of x. And essentially, that's what the first fundamental theorem is claiming. Okay? Meron pang isang additional claim, yung section A ng FTC. Sinasabi niya din na si capital F ay continuously differentiable. Pag sinabi natin continuously differentiable, ibig sabihin si capital F ay continuous at saka si F prime ay continuous din. Right? Yun yung pagiging continuously differentiable. Usual notation natin doon ay F is C2. Ibig sabihin si F at saka yung first derivative niya ay continuous din. And I think that is one nice exercise that you can do. Yeah. Iniwan na siya as an exercise ni lecture notes. All right? Now let's push forward and try to prove section B. Ano naman ang sinasabi ng section B? Ito yung pag-evaluate ng value ng definite integral using the function values of the antiderivatives at the top and the bottom boundary. Tingnan natin kung bakit totoo yan. Now, what we will do is to consider a regular partition inducer of the interval AB. So ito yung mga ito yung partition inducer natin. Okay. We will assume that they are regularly spaced, meaning actually mali ito. Nabago ko na to dun sa bagong version. Ito dapat ay delta x sub I ay equal kay b minus a over n for all I. Kasi gusto ko ay regular yung partition. So I'm not sure if that will matter too much. Actually, parang pwedeng hindi nga regular partition. Tingnan lang natin kung aaser nga ba siya. But for now, let's think of P sub n to be a regular partition. Okay? Now, i-apply ko yung mean value theorem for derivatives kay capital F. Okay? So ano nga ba yung sinasabi ng mean value theorem for derivatives? F is differentiable. So, ibig sabihin, there will exist a number C in the open interval AB such that f prime of C ay equals f of B minus f of A all over B minus A. Ito yung sinasabi ng mean value theorem for derivatives. There exists a point on the on the open interval AB such that the slope of the tangent line is equal to the slope of the secant line. All right? Tapos ito ay gagamitin ko, okay? Ito ay gagamitin ko sa mga maliliit na intervals na nanggagaling dun sa partition inducer P sub n. So I will apply it to the first subinterval, the subinterval x0 to x1. So ang A ko ay x sub 0, ang B ko ay x1. Right? So there exists a number, let's call it C1, on that open subinterval, right? Such that the function value, actually ang ginawa na pala doon ay kinross multiply na. So yung length ng interval na multiply na siya dun sa derivative. And that's how you got this product over here. Okay, cross multiplication lang ng MVT. And do it for all of the other subintervals. Okay. Tapos sinulat niya lang yung delta x1, delta x2, sila yung x1 minus x0. All right? Do this for all possible subintervals so formed, the sunod-sunod sila. So x0 to x1, susunod x1 to x2, x2 to x3, and so on. All right? Then what we will do is to add all of the left-hand sides and all the right-hand sides of this equation. Okay? Anong mangyayari pag inadd ko lahat ng mga nasa left-hand side ng equation? Pag inadd ko sila, ay si f of x sub 1 makakancel. Si f of x2 makakancel siya nung nandun. Si f sub x sub n minus 1, makakancel siya nito. So essentially, this will be a telescoping sum, leaving us only with the first term and the last term. All right? So it's going to be f of x sub n minus f of x sub 0. But we assume that P sub n is a partition inducer. Therefore, x sub 0 is equal to A, and x sub n is equal to B. So that's how we got this guy. Alright? Siya yung equal dito. Tapos, i-add naman natin yung mga right-hand sides. And we can write it in a clean summation notation like this. But this should look familiar. This is basically the definition of a Riemann sum. So ito ay magiging Riemann sum. And I think you know what will happen next. Gusto ko mapakita na ito ay equals sa definite integral. So kailangan mapakita ko to ay equals sa definite integral. So ang kailangan kong gawin ay kunin yung limit ng both sides as n approaches positive infinity. Kasi pag kinuha ko yung limit nito as n approaches positive infinity, this guy will be actually the Riemann integral of f over the interval AB by Darboux's theorem, section 3. Right? Tapos, ang f of b at saka f of a naman ay mga constants. They don't depend on n. No matter how many subintervals we consider, b is still b, a is equal to a, this will be unchanged. So, ibig sabihin, napakita na natin na yung integral ni f over the interval ab ay equals sa capital F of b minus capital F of a, which ends the proof. Okay? And it doesn't just end the proof, it ends Math 155 for us this semester. Okay? Finally. Medyo nakakapagod yung lecture ngayon. But hopefully kahit medyo mabilis, you guys got something from this discussion. All right? So, do you guys have any questions? Sulitin nyo na kasi ito na yung last meeting natin. Hindi ko na kayo hahanapin sa Tuesday. But I will still be free for consultation. So if you have some questions about the problem set, so just hit me up with an email or a chat via MS Teams. We can meet on Monday or Tuesday, 1 to 3 p.m. Tapos sa Tuesday, pwede pa rin ako makapag-meet sa inyo ng 4 to 5:30. But we won't have any formal class anymore. So it is on a need. It is on need basis. So kung kailangan nyo makipag-meet sa akin, I will be more than happy to meet with you. Especially kasi meron pa tayong problem set na tinatapos. But aside from that, any questions? Do you want to say something? All right, so kung wala naman, so I guess this is goodbye for Math 155 for us, but hopefully not a goodbye for us personally. Ano ba kayo, mga juniors or seniors? So maybe we will still meet somewhere along the road. Especially you are math majors, so meron pa mga ilang sems, I might be your professors, or when the face-to-face classes come back, hopefully soon, we can meet in person. Tapos pakilala lang kayo, sir, ako yung nakikita mong thumbnail dun sa MS Teams. All right. So yeah, because I really enjoyed this class. Hopefully you did so. Sana may mga napulot kayo na kahit na maliliit na mga bagay from our class. And it was nice having you as my students. So yeah, goodbye for now, but see you around. Okay. Bye, guys.
Thank you, sir.
Mhm.
Thank you, sir.
All right.